this episode, we would like to say that in the spirit of reconciliation, that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community.
Hi everyone, welcome to another episode of Spaghettification podcast. My name's AstroStephi.
And I'm the Drunk Astronomer. So it's my turn to interview you now. So you asked me what got me into astronomy. I'm going to ask you the same question. Where did your passion, your love for all things astrophysics and your job, I guess, essentially, how did you get to where you are now? Like, where did it start?
Yeah, so when I was a kid, I don't exactly remember where it came from, but I do have some memories, which is one of them is when I was in year 2, I got a little book, like sort of this big board book, which had information on all the planets in it. And I read that, I shredded that book. I read it so much. It was my like show and tell thing one week. I really, really loved it. And so then as I sort of kept getting older, and I would just read all the time when I was a kid, and I read a lot of space books and read just everything I could get my hands on, basically. So, the local library, I read all of the books that they had on space there in Newcastle. And so I I think the idea of actually doing it for a job was I went to Parkes, the radio telescope, when I was probably 10-ish, around that sort of age, because my parents were doctors. We would go to conferences sort of around New South Wales occasionally, and one of them took us sort of close to Parkes, and so we went to visit there. And so seeing that was really cool. And the visitor centre there at that time, they were playing a movie about quasars, and I was just like, what are these things? I've never heard about them before. So definitely by the time I was sort of year 5, 6, I was like, I want to be an astronomer. And so then as I went through school, I was very good at science and maths, which was good. And then when we moved to Melbourne when I was in year 10, I did work experience in the Astro group. We had, at that point, it was more sort of, we did a lot of talks from the PhD students and a few like lab activities, which is sort of what we do now, but we've tried to make it a bit more like what is a week in astronomy like? But I still thought it was really cool. Like, I learned about neutron stars and superfluids and all sorts of things like that for the first time. And so I got home at the end of that week and was very sad that I still had 2.5 years of high school left that I had to do before I could go to university. So
I want to go to uni.
Yeah. So when I was in year 11 and 12, I was working in a pharmacy. So I sort of had an idea that maybe I would be a pharmacist.
Did you work in pharmacy as well?
Yeah, because my dad worked at the GP surgery next door. And so I didn't want to be a doctor because that is a very hard job, and I didn't want to do that.
So can I ask a side question? Were you a drug dealer as well?
No.
Because I was. I worked in a pharmacy as well when I was 15, 16, and I would ride and deliver prescriptions to the retired people at the aged care facilities around the suburb. Like, I was literally a drug dealer.
No, I only worked in the shop in Werribee. I think the drug dealers were probably all outside at the bus stop. But yeah, so I thought about doing pharmacy for a bit. But sort of when I was doing my uni preferences, put science first. And so did science at Melbourne Uni, where I majored in physics and sort of did a lot of maths as well. Didn't end up doing mathematical physics in the end, because I sort of got to third year maths and was just like, no, I'm tired of this. Just let me finish.
I just want to get out and do work.
Yeah. So yeah, I did that. And then in between doing, so my undergrad I did 4 years, because I did a diploma in languages as well, which at Melbourne is something you can do. You do like a a degree in physics, and then we have this thing called breadth subjects, which is where you do subjects that are not part of science as part of your degree. And so you can sort of take those breadth subjects and do them into third year as well and get an extra diploma on the side, basically. So I did sort of 3.5 years worth of subjects in 4 years. So my final year I had a bit of free time. And what I did was I actually worked at Swinburne doing a short research project with Jeff Cookie, which was all about supernovae in the early universe. So basically there was a bunch of archival data from the CFHT telescope in Hawaii, which is the Canada-France-Hawaii telescope. So they've done this big survey basically looking at 4 patches of the sky for a really long time. And this is like years worth of data. And there were other parts of the survey, but the deep stuff was what we were interested in, because as you get further into the universe, things get fainter and fainter. So looking for supernovae, which are things that are very bright intrinsically, but again, as you're getting further and further out in the universe, they're getting fainter and fainter, but also they don't last a very long time. So if you stack all of the light that the supernova emits, then it appears a bit brighter in your image and makes them easier to find. So what we wanted to do was to basically try and find these really distant galaxies, which we did using this thing called alignment break technique, which is sort of what I do with my PhD. So basically you're looking for really red objects in your image, because as things get further away from us, the light gets redshifted. And so neutral hydrogen in the universe, which is just basically hydrogen gas, it absorbs all of the blue light basically that those stars are emitting and galaxies. And so you're just looking for red things, and redder basically gives you further and further away things. So what I do for my PhD, we need space telescopes for, but what I was doing for this project, we could do with ground-based telescopes, because if you're looking at things that are about 3 to 4 billion years after the Big Bang, that red light that you're looking for is still at optical wavelengths. So a beautiful data set, looking for these galaxies. And what we were looking for actually was the supernovae that didn't have galaxies. So either the galaxy itself is just so faint and small that we can't see it, and so this supernova is coming from either just a really dwarfy galaxy, or just even a cluster of stars maybe, or some gas that it's sort of been one of the first stars to form in, or it's occurred on the outskirts of a galaxy, and we have... That's the tricky part. I'm happy to talk about that. But so maybe it's on the outskirts of a galaxy, because when we look at galaxies in images, we see the brightest central parts of the galaxy, but we know that as we look further and further, they get bigger and bigger. Basically, there's more and more stars out from a galaxy the deeper you look into it. And we can see this really nicely with the Andromeda galaxy, where even with things like Hubble, you see a lot more of the galaxy than you see with your naked eye. But if you do like really deep imaging around Andromeda, it goes out for degrees and degrees basically on the sky. It's huge.
It's massive.
Yeah.
But it's not as big as the Milky Way.
Sorry?
It's not as big as the Milky Way, is
No,
it?
it's bigger. It's bigger.
I thought there were recent studies showing that it's not bigger than the Milky Way, that the Milky Way is bigger than Andromeda.
No, I think Andromeda's bigger.
They lied to me.
It's got more stars, definitely. Or a bigger mass of stars. So, yeah, so looking for these weird supernovae. And so there's a lot of evidence that the environment that a supernova comes from gives you different properties of the supernova itself. And this is because those environment basically refers to the galaxy that it grew up in. So if you have a galaxy which is really young, the stars inside it are really young, and so you're going to get a particular sort of supernova. If you have older stars, which give you type 1a supernovae, which are the ones that we use for cosmology, maybe you have a really metal-rich environment, which basically means that you've had lots and lots of stars forming, and they give you lots of elements that are heavier than helium. So that may give you a different sort of supernova. And supernovae are extremely complicated things. Trying to model them is just insane. It's like you have so much going on with the different elements give you different ways that it might explode. Different masses of stars give you different explosion mechanisms, so all sorts of things. So what we were looking for was trying to find these furthest away ones more as proof of concept than actually being able to study them, because this was archival data. So those supernovae had disappeared and we wouldn't be able to go and follow them up. But the idea was to make this work so that for future supernova surveys, you could find these orphan supernovae really efficiently. So that was what led into my master's research. So I did my master's at Melbourne Uni, but I was co-supervised by Jeff Cookie at Swinburne, continuing this project on.
How good is Jeff?
He's so good, yes. Yeah. So at that point, he had only been in Melbourne for a few years, so he wasn't super busy like he is now.
He's really busy now.
He's so busy, and he just he says yes to everything, and he just has this real joy of all the different things that he does. So when I was working with him, he was just getting into fast radio bursts. So they were a pretty new thing back then. This was in 2012, 2013. And so this was the very early stages of planning the Deeper, Wider, Faster survey. But yeah, it was really exciting, I think, and it really gave me a love of the early universe sort of stuff, not just because it's really hard to look at, but also because the universe was different then. So what was different? So if we could find these supernovae, we could tell a bit about the different sorts of stars that were in the early universe. So I finished my master's and I started a PhD at Melbourne Uni, and there I worked with Michele Trenti. And at that point, he had just moved to Melbourne as well, so I was one of his first students to start. And that project was sort of following on when I was in my second year of master's. I went to the Vatican Observatory in Italy and did a summer school there. Yeah. And so that's located a bit outside of Rome in Albano Laziale. And so there's a basically an observatory run by Jesuit priests, and they are close to the Pope's summer palace, basically. So every 2 years, until COVID, they would do a summer school where they would bring students from all over the world to the observatory, and we learned about galaxies, all sorts of different things about galaxies. We were there for a month, but we also did a short research project there with one of the faculty. So I did mine with Michele on galaxies also in the early universe, but now even further back into the universe. So if the supernovae we're looking for were in the first 3 billion years of the universe, these are in the first 500 to 700 million years. So when you get to that level of redshift, you have to look at the infrared. And this is a big part of what JWST is doing. We talked about that with Maddie in that episode. Go listen. Because infrared light just doesn't reach Earth because it gets absorbed by our atmosphere. So you need space telescopes to do it. So Michele has a huge Hubble telescope program called the Brightest of Reionizing Galaxies program, which is with Hubble, but in a really cool way. So what he did was, with Hubble, you have your focal plane, and that has your instrument that you're looking at, whatever particular target you want to look at with. But also in that focal plane, you can fit another instrument in. So you can take two sets of observations at the same time. So you're not looking at exactly the same patch of sky. But for us, it's actually really good because when you want to look at galaxies in the early universe, you have a lot of clustering. And so we know that galaxies in our local universe are clustered.
Do you know what, just before you get back into it, do you know what's really funny? We're talking about how your journey into the field of astrophysics and astronomy, and you've answered all my next lots of questions.
Sorry, this is what happens when you just let me.
Just flowing.
So Hubble, it can take images with two different instruments at the same time. And so when you're looking for galaxies in the very early universe, galaxies are clustered, and this is an effect of dark matter and how the universe formed originally. So actually measuring how much galaxies are clustered is really important for us to understand how the universe formed and all of its different properties. But it does mean that if you're looking for these really rare, really faint galaxies in the early universe, if you look at one patch of sky, you might be lucky enough to see a bunch of them because there's a cluster there, or you might just see nothing because there's no cluster there. So if you're looking at random patches of the sky, which you're not determining, they're just based on, there's an interesting quasar a couple of degrees away that someone else is looking at, I'm going to get this time, which is bonus time, essentially with Hubble, that you're maximizing the use of this expensive telescope that everyone really wants to get time on.
I want to get time on it.
You can get a huge amount of data, not for free, but very cheaply. And so the Brightest of Reionizing Galaxies survey is using that sort of approach to get a lot of data that is useful for looking at galaxies in the early universe. And so what we were doing was trying to see with the first lot of data, because that was optimized to find galaxies 700 to 800 million years after the Big Bang. And all of these numbers are going to sound really like, why are you going to search 200 million years back or 200 million years forward? But the early universe has a lot of different things happening. So you have the Big Bang, then you have it inflating until it's cold enough that the first light is released. And this is the cosmic microwave background, which I don't think we've had anyone talking about yet on the podcast, but I know people that I will.
And we should.
I will get people. So this is a radio signal that we see these days, but when it was emitted, it was very high energy light because this is from all of those hydrogen, helium, a few other element molecules. All of the light is being bounced around this really, really hot gas. And so it suddenly gets released into the universe, and then everything just cools down basically for a while. So to form stars, you need cool gas. You can't have hot gas. And so everything had to cool down enough for those first stars to form. So once that starts to happen, this is around 100 million years or so after the Big Bang, then you can start to get the first stars forming. And once you have enough of the first stars, then you get those first galaxies forming. So we think this is starting to happen around 400 million years after the Big Bang. With Hubble, you can get into the infrared enough to see galaxies around 500 million years after the Big Bang. So the data that we had, though, in this first set of data just wasn't quite good enough to find galaxies in this really early range because you want as much data at this really red end as possible. So Hubble is just limited. So the next set of data was a bit redesigned so that it was a bit more efficient at getting these galaxies in the really early universe. And then so it's been quite successful in finding candidates of galaxies, and we're very careful that because really you're just looking at the light from the galaxy in an image, you can't do spectroscopy of any of these galaxies until James Webb. So when I was doing my PhD, it was technically possible because Hubble can do something called Grism spectroscopy, which is slitless spectroscopy. So you get a spectrum of everything in the image, but because you're looking for the very, very faintest things in these images, and you've got all sorts of bright stars, galaxies from closer to us in the way, getting those spectra are really difficult. You have to be very, very lucky to be able to get a spectrum for any given object. So we were looking at the images, and then we went to Spitzer to try and get some more infrared data. But Spitzer is a wonderful telescope, and we miss it dearly, but it's not very big. It's about 1 meter in diameter. So its resolution is just not very good compared to Hubble, especially because Hubble has amazing resolution. It's a 2.4 meter mirror in space. It's above the atmosphere. You don't have problems with seeing. It's beautiful. So Spitzer, no light pollution, except for the sun. But
bloody sun.
Yeah. So with Spitzer, what we were really trying to do was say, okay, if we do see something in Spitzer, then it must be something which is closer to us that just looks like one of our early universe galaxies, because those closer to us galaxies, they would be much brighter in the infrared, because galaxies tend to get brighter in the infrared than one of our early galaxies where we're still looking at the rest frame optical, which would be much fainter. So we use Spitzer to try and rule things out, but now that James Webb is finally launched and we can actually get proper spectra of these galaxies, there was one example that was in this first data release, which was a galaxy at what we call redshift 8. So this is around 13 billion years away from us, but around 700 million years after the Big Bang. So in that sort of age range of what we're looking at, and you can see all sorts of different chemicals in that galaxy. You can see hydrogen, oxygen, and neon. And this is basically unheard of before JWST. So I'm not really working in astronomy research anymore, but this is a really amazing time for people in my field because there's just going to be so much data on all these different galaxies. So we can go from finding galaxy candidates at this really early time to actually confirming them, but then also seeing what sorts of chemicals are in them, how bright are they at different wavelengths, what sorts of stars are in them, how fast are they forming galaxies, and this is going to really change our view of, it will either change or it will confirm our view of how the early universe was different from what we see in the universe today. Like in our Milky Way, the Milky Way is quite an old galaxy. It's around 10 billion years old. It's got a lot of life left in it, and that's much, much older than these galaxies, which are only a few 100 million years old. So we think they're going to be much different. They're also evolving in a different universe in general, where there's not as much like heavier elements around. So that's going to change the sorts of stars. So what I wanted to be doing when I was sort of in the beginning of my PhD was looking for supernovae in these really distant galaxies, which was just impossible to do at that point because Hubble could barely see these galaxies, but trying to get any sort of time series data on them was going to be impossible. But I think that is possible now with JWST. You'd have to be very lucky because supernovae are very rare objects in general, so you have to look at a lot of galaxies for a while to catch them. But I have confidence that people will be able to do it now, and I'm really excited to see what it can do. Because if you can find particular sorts of supernovae that only occur from really massive stars that have very low, what we call contamination. So if the stars are mostly just hydrogen and helium, nothing from stars that have formed earlier, we think you're going to get some really impressive explosions, and I'm hoping that will come out of it. So yeah, that's sort of my journey in astronomy. And so then beyond that, I've been on leave from my PhD for a few years because I had a lot of health problems and things. So what I've been doing is teaching astronomy at Melbourne Uni, and I love that. I do third years, which is what I've been doing for a really long time, where we teach them how to do astronomy research. Basically, we teach them how to do simulations where they simulate the Earth, the Sun, and a black hole, and how they would sort of interact with each other with different initial parameters that you put into the code. But then also, how do you actually make a telescope observing plan? How do you execute it? How do you analyze images from a telescope? So that's one of my favorite things is when we get the images and the students get to look at them and like, you chose those galaxies. And then I also teach first year. So I coordinate first year labs in first semester where we learn about spectroscopy basically, and then Hubble's law, so how the universe is expanding, how galaxies are moving away from each other. And then we do a little bit about exoplanets and life on other planets, which when I started teaching, I was like, this isn't really super scientific, but I've sort of come around to it over time. And then teach second semester where we do a big astro subject. So we start from orbits and things, and how does gravity make things move in the universe through like the solar system, and then out to stars and galaxies and things. So that's really fun. And then just this year, I have gotten jobs at the Victorian Space Science Education Centre, or VSEC, which is where we have school kids come in and do experiments. And they do they go to Mars, so they get dressed up in flight suits and they do experiments and they take samples of Mars and analyze them.
I want to come and do that.
It's pretty cool. I don't think they do it for adults.
I need to organise to come and film out there, to do a YouTube video out there.
Yes, put that in the email that you're sending me.
Yeah, I'm going to. It'll be separate to other stuff, but I think that'd be so friggin' cool.
Yeah. And the room there is really cool. Like when you go through the doors and you step out onto the Mars surface and you're like, yeah, okay. Like, I get it.
I'm up for that.
And so that's really fun. So that's a big day because you have a school will come in and you'll have, say, 60 kids or something. And you split them up into 4 groups and they do 3 different activities during the day. So, you're sort of running around all day talking to the kids. But it's really fun. And then I also work at ScienceWorks, which I really love, which is where I do shows and things. So I do lightning room shows, talking about energy and different sorts of energy that we use in our daily lives and how one sort of energy transforms into another. And then do the big lightning show at the end, which is always fun. And then I also do planetarium shows. So we show a video, and then at the end I talk a bit about what's in the sky tonight, and then sort of go from zoom out to the whole Milky Way and then some nearby galaxies. And I really love that because it's the planetarium, I think, is just an amazing way to get people to view astronomy and things in a different way, because you can literally just fly through the stars, which is awesome. So lots of different things.
I want to come back to the Vatican stuff.
Yes,
because as most people who know me know how vocal I am about religion, and I find it really weird, and always have, because I've known about the Vatican Observatory and that, and it confuses the crap out of me. That people, well, religions, not people, won't say people, I'll say religions that believe the Earth was formed 6,000 years ago. When I want to know how does it work with them. I mean, it's cool that they've got it, and I love that they're doing that. But does that not conflict directly with their own beliefs?
No, so the younger sort of beliefs that you're talking about are not necessarily Catholic beliefs. So I actually went to school in Hoppers Crossing here in Melbourne, and we got taught creationism and young Earth creationism, and that was a Baptist school. So that sort of line of thought is really more of a it's sort of a new belief, honestly. So we know that when evolution was sort of first being developed in the 1800s, there was a lot of debate about how old the Earth was, and sort of geology also coming in and saying, actually, things are really, really old. But the Vatican, as far as I know, they actually sort of took that all in their stride as much as anyone. And so, as the evidence came in, it was, they sort of have adapted that into their worldview. So, definitely, like people like, what was his name? I mean, I'm not a defender of the Catholic Church, I will say. My family is very Catholic, but
Look,
no.
I was raised Roman Catholic, so
Yeah,
like my
I wasn't
grandparents,
raised
like,
Catholic.
I did Sunday school, reconciliation, confirmation, all those sorts of things.
Yeah, yeah. So the Vatican Observatory um is run by Jesuit priests. I don't know if they're all Jesuits. I think they are all Jesuits, but certainly the ones that we talked to were. And so the Vatican Observatory has a really long history. So it was because, and I think this is one of the things that I've really sort of gotten more aware of, I would say, as I'm moving more into sort of science communication, is that before our modern era, like looking at the stars and the sky was just something that everyone did every day, because there was no light apart from fires and candles and things. And people use the sky to tell them all about the time of year it was. If you see this star in the sky just after the sun sets, oh, that means we're getting into summer, or or things like that. So I think this the Vatican Observatory is just sort of part of that tradition where you had court astronomers telling you about things, and if things were changing, if you saw a supernova in the sky or you saw a comet, what does that mean? And so there's sort of astronomy and sort of prophecy, I think, were very linked for a very long time. So the Vatican Observatory has been around for a long time. I think definitely since at least the 1500s, but maybe unofficially even before then. And so the Vatican Observatory has been staffed since the 1700s, and they did some important work. So they're very proud of Father Angelo Secchi. I forget how you pronounce it. And so he was the director, and they had a big star catalog that they were making there, and so pinpointing sort of all the locations of the stars. So there was work done there, and then these days there's research that goes on there. So they have a group which looks at meteorites, and sort of you can find meteorites on the Earth. A good place to find them is actually in Antarctica, because meteorites fall all over the Earth, but they tend to sort of get mixed up with the Earth's general sort of crust and things. But in Antarctica, they just sort of stay on the top of the snow, and so they're also very dark, so you can see them against the white snow really easily. So you collect meteorites in Antarctica, bring them back to the observatory, and then you can look at actually what sort of elements they have in them. And so one of the cool things I learned when I was there is that actually when we look at the elements that are in meteorites, that doesn't necessarily match up with our idea of how the solar system formed, which was a big cloud of gas and dust, which got sort of grains of dust that sort of gradually gravitationally created and formed the planets and things, and then everything that was left over became meteorites and asteroids and things. So yeah, studying these meteorites is something they do there, and it's really cool. So yeah, it's in terms of how they combine religion and astronomy. I think in general they do their research with a very sort of scientific frame of mind, and then I think the religion part is just personal for each of the brothers that work there. So we got to meet the Pope when we were there, because at that point
who was Pope at that time?
it was still Francis.
I'm still saying what? Oh, okay.
Yeah. So the head of the Vatican, or director of the observatory at that point, was when he was training as a Jesuit in Argentina, his sort of mentor brother was actually the Pope, and so they're still close friends now that they both live in Rome, I guess. So yeah, they arranged a meeting for us, and so yeah, the Pope was very nice and was like, "You guys are really cool," basically, and studying astronomy.
What was he like to meet?
We only really met him as just sort of a handshake, and he
okay,
sort of moved on, but
still cool.
Yeah, he gave us an audience, which is very cool. Yeah,
it is an awesome experience.
Yeah,
to have to go over to a place like that. That's why I wanted to come back to it, because I just wanted. I've seen so much of their stuff floating around.
Yes.
But yeah, look, that's such a seriously cool thing to have experienced, and I was like, I've heard about them, I know about them.
Yeah.
I don't know a great deal about them, but now I do, and now our listeners do as well, and that's what's really cool about it. It's like, that's an experience that not many people would get to have.
Definitely not.
It's part of your journey.
To go, getting to go into the all sorts of different places that are, like, we went to the Pope's summer palace, Castle Gandolfo, and got to see the gardens there, and so yeah, it was very special. I've got lots of photos of it. I can give you the link as well if you want to.
That'd be very cool.
But yeah, the current director of the observatory, Guy Consimano, is very like chatty and loud and talkative, and apparently he was actually in, I think, Angels and Demons or Da Vinci Code or something.
Okay. Oh, that's cool.
Research book sort of talks about him in so yeah. We could definitely try and get one of them on, one of the brothers. I think that would be great. Although it's been a long time, I don't know if they would remember me. They apparently have a podcast too. There we go. Yes.
I want to jump across to, because you kind of killed all the questions, because
I just talked.
Went on this awesome run and just explained everything in great detail. But I want to go back over to Science Works, and how that one came about, and I guess your passion for what I would call outreach as well.
Mm-hmm. Yeah,
Tell us a little bit about that.
Yeah, so I started doing outreach when I was in undergrad. So when I started uni, I was very shy. I was 17 actually when I started uni, because I started school early, and it's just very shy. So when I was in second year, I was like, I want to do some things. I want to get some practice, and so I started doing telescopes in schools, which is a program where undergraduates from a few different universities around Melbourne are put in touch with teachers at schools, and so you go in and you do a couple of classes a week. 2 classes a week was what I would do when they're doing their regular science classes, and you would help out with doing experiments or giving them a talk or doing Q&A, that sort of thing. So I started off with year 9 students, and the first school I was at, it was mostly more sort of helping them with questions, but also they had some experiments that they were scheduled to do, so I helped out with those. And then second school I was at, it was year 9 students again, and so the teacher there was like, what do you want to do? And so I sort of had a few ideas for some different experiments that related to what they were doing. And then when I got to my second year doing it, I started off with year 5 and 6 students. And so there, the teacher really was just like, I'm putting, whatever content, you're going to do this. So I had a look in the, the sort of cupboard where they had a bunch of equipment, and I was like, okay, we can use this, we can use this, we can use this. And so, so at that point, I still wasn't very good at giving being loud enough to control a group of 25, 8-year-olds or 9. No, you 5, 6. They're probably more like 10-year-olds. So the teacher would still very much be like in control, but I would be going through the experiment with them. And that was really fun. So we did all sorts of things. We did like the M&M's experiment where you get the colors to sort of rain out of the dye of the shell. And you can do like the, what do you call it? Where the colors sort of run up and you can see which colors are in, like which underlying colors are in the different colors of dye. Starts with C. I forget what it's called. And then we did some electronics ones where we made some circuits and we made a little switch and I taught them about Morse code. And so we could send messages with the switch making a noise. And so that was really fun. And so then my last one that I did, which was a year 3 to 6 class, and they were doing little research projects that they were designing. So it was like, how fast do plants grow or some stuff like that. So when I went in, I would help them out with what they were doing. And then my biggest memory from that was, I think it was just the year 3 students maybe, or the year 3 and 4, but we decided that we would do a Q&A session about astronomy. And it just immediately devolved into them asking me about black holes for like an hour. So yeah, then I started working with telescopes in schools, which at that point was very new. It was sort of the first year that it was starting. And so I was one of the first students to help out. So with that program, what the University of Melbourne was doing was they had funding to buy a bunch of 12-inch Meade telescopes, and they would loan them out to schools for 3 years. And so the schools would then use them for observing nights. And so we would go in as students to help them out with the telescopes and answer questions from students. And if it was cloudy, give talks or watch movies and things with them. So I did that for a long time. I did that from 2012 until about 2017 when I just sort of didn't have time for it. And so that's when I started working with Claire Kenyon, who is our sadly missed former host of the podcast.
We got to get her back.
Well, she's got a new job. Have you seen?
Yeah, I have, yeah.
She's going to be working on podcasts for the Royal Institute of Science in Australia, so that's really amazing.
Working on Cosmos or something, yeah.
Yeah. So yeah, I did that. I did that for a long time, and then so it's just been very involved in outreach, and I've done a lot of different sorts of things at Melbourne Uni as well, like organising different things. I worked in women in physics sort of a lot, and women in science and engineering more general at Melbourne Uni, doing a lot of events, sort of trying to build a network of students and researchers there. And so then when I did my ScienceWorks interview, I didn't get a job the first time I interviewed, but the second time I did manage to get a position as a presenter there. So
pretty cool job.
Yeah, it's really great. I enjoy it a lot. And now I have a huge amount of ideas for things to do and have to be like, no, I've only been there a few months. I have to wait and learn like everything before I can do anything. So
where do you see yourself in the world of astronomy and outreach in the next 5 years? Like, what are your dreams?
What I would love to be doing is doing sort of outreach, but also staying sort of connected to the universities. So, one thing that I love my fellow science communicators and things, but one thing I have found is that having a really deep knowledge base in astronomy is really helpful for me, even if I'm just explaining the basics, and actually being able to get that information out there. And so what I would love to be doing is I have this idea I know that we are producing a new show. This is a bit of a spoiler alert, but a new show hopefully coming out next year, which is a presenter-led tour through the solar system. So we have one of these at the moment at ScienceWorks at the planetarium.
So this is at the planetarium, is it? Or is this different?
No, this is at planetarium. Yeah, so
cool.
we have one which is called Ticket to the Universe, which is where you start from the Earth and you basically go out in the universe from the Earth to the cosmic macro background.
I've seen that one. That's been around for a while.
It's been around for a while, yeah. So I really enjoy it. So we're making a new version of that for National Science Week this year, which is about rare things, because the theme of National Science Week this year is rare. So I've put some suggestions into Tanya Hill of things that we could include there. Next year, hopefully there'll be a new show which is about the solar system, because there's so much you can do at the planetarium. So one of the things I'd love to do is be able to take those sorts of trips through the solar system, see if we could get undergrads, high school students in to really see this sort of stuff that they're learning about in front of their eyes. I think that's just such a really good way of cementing those things, because one thing I find that at university, you might have students who at the very end of the semester are still confused about the difference between a planet and a star and a galaxy. And it's really disheartening to get to the end of teaching them for all this time, and there's still these basic misconceptions. But if you can say, these are the planets, they are orbiting around the star, can you see it? And, all of these stars are inside this galaxy. I think it's really, I think that would be really awesome. Of course, getting that many students into the planetarium for like a once a year show or something is not very cost effective. So whether it could actually happen, I don't know. But yeah,
Watch
really sort
space.
of, trying to get more connections between us and the university and all the people who are already doing outreach, because, we have outreach programs that we've been running for a really long time. So Claire Kenyon, our, as I said, beloved former host, ran telescopes in schools, and she was our LAB teaching outreach fellow for a long time at Melbourne Uni in the Astro group. And she is a former teacher herself, so she has a really good grounding in how students learn and things.
She's very entertaining as well.
She is, but there's a lot further that you could take a lot of the ideas that she had as well than she was able to take them in the time that she had in that role. So definitely lots of things that I want to do. I have just a head full of ideas that I try to write down. Mark gets some of them in his Instagram messenger. But things like, because a lot of our teaching materials at Melbourne Uni as well are quite old. So there are some things that I did when I was in work experience in 2006 that are still sort of the backbone of the activities that we do today, because there's just no funding to revamp them as much as we would like. So really getting in and updating these labs and getting our students' idea of, okay, well, what is doing astronomy actually like? Because there's all sorts of different things we could do. So at VSEC, they also have a radio telescope. I know you guys at the ASV have a radio telescope.
We do. We have an 8.5 meter one.
Yeah, and so there's just nothing about radio astronomy in our curriculum, as far as I know. And it's a huge thing in Australia. And Rachel Webster, who's one of our astro people, has had a huge hand in sort of developing radio astronomy over the last 30 years in Australia. But we don't teach our students about it. So, all sorts of different teaching and education things that I would like to be doing. And I think that's really sort of where I want to stay, at least for the next bit. So if you have funding, I would love to have it so that I can do fun astro development stuff
too. Since you asked me about my favorite thing to view an image, I want to ask you about your favorite object to study.
Good question. Yeah, so
because you've done a lot of study and research on different objects in different parts of the universe. Which one is your favorite?
Yeah, I think if I had ended up applying for postdocs as the standard sort of academic career would have entailed, what I would have loved to be doing was, as I sort of mentioned before, looking for these supernovae that happened in the really early universe, because I think there's so much you can get from them, and it's just been impossible basically until now, and maybe it's still even impossible now, but there's more space telescopes that are planned and in the current process of being developed, like the Nancy Roman Space Telescope, that will really be able to get a much better view on these sort of things. So especially looking for them in the early universe, because they are such a great direct probe of star formation. So star formation, we have our general idea of how it works. In the local universe, in the Milky Way, we can look at regions like the Orion Nebula. We can look at the Eagle Nebula. We can look at the Tarantula Nebula. These are all the areas where stars are forming. Young stars are forming, but they're forming from material that has had, 13 billion years worth of previous stars coming and making heavier elements and what we call enriching that gas, so making that gas more full of elements other than hydrogen and helium. Yeah. Whereas as I said, in the early universe, we think it's a lot different. There hasn't been all that time for these processes to happen. So being able to see them will tell us what sorts of stars were there. Seeing if we can see these really rare hypothetical sorts of supernovae from really massive stars, because how big the first stars were is sort of an open question. When we first started thinking about them, 20, 30 years ago, these are called population 3 stars. And so the idea then was that they would be supermassive. They would be hundreds solar masses. Because they're forming from this really pristine material, which doesn't have a lot of these extra elements that make stars form faster. And so if you're forming the star for a longer time, you can get it to build more and more mass before it turns on and becomes a star. It stops forming. So once you update your models, though, and include all sorts of different physics, and even if you go from what we call a 2D model to a 3D model, or if you make the model spin around, that all changes how the stuff inside the star gets mixed up or inside the gas cloud that's forming the star changes. And so then we thought that maybe they would stop forming sooner, and so they would only get to maybe 30 or 40 solar masses, and they will produce different sorts of supernovae, these supermassive, like 100 solar mass stars, and these very massive 30 to 40 mass stars. So seeing those sort of things gives you different ideas. And then you can also use the light from the supernovae to tell you about, as I said, the environment where they grow up in. What is the gas around them like? Because you can look for particular absorption features from the gas around them eating up some of that light. So you can tell a bit about what's actually there in a way that you can't do without like a super, super, super high resolution telescope that we're never going to be able to build. So, yeah, all sorts of interesting things, I think, but you'd have to just be super lucky to find them. You could spend, and with Deeper, Wider, Faster, the first years of this program where there were, a dozen telescopes or something all looking at patches of the same sky at the same time, waiting for a fast radio burst to happen so that we were in place to go to that patch of sky to look at it as soon as it happened. And just one never went off. And so you can do all sorts of other things with that data. But
they might have gone off. You just might not have been able to see them.
Well, we were using Parkes, which was the big fast radio burst finder at the time. So, if we had seen one. But this is the thing about looking for mysterious objects that you don't know about. You don't know if they're more likely to be in the galaxy or out of the galaxy or all sorts.
How far away they are, how close they are, how big, bright they're going to be.
Yeah.
Are they going to be hidden by something that's in the way?
Yeah. yeah. So, I think I love my early galaxies, and they are much easier to study than supernovae are. But I think if I could have taken that next step to try and marry the two fields together, that would have been what I would have loved to do. But it's just a hard game. Being an observer is tricky because you're always trying to get more observing time. And so to do that, you have to put proposals in. You have to justify why you want to use that particular telescope. You have to justify the science that you want to do with it. Why is this interesting enough to be worth using the telescope for? Why do I want to use it at this particular time and this particular set of filters and things? And it takes a lot of time. So like Jeff Cookie would spend, a month a year basically just writing these proposals for telescope time. And then, and then you have to analyze it and you have to, maybe you get what you were looking for. That's great. But maybe you don't get what you're looking for. And you're like, oh, okay, well now I have to rethink everything. What am I going to do instead? And start again. So it's a hard game. And I realized that I'm much happier talking about it to people than actually doing it. So
let the others do it then. Have fun.
People like Maddie that we talked to last week. She loves doing the research and she loves writing the papers and she loves she was chatting with me about I've got JWST quasar data for the first time and And, generacy data is beautiful. We talked about it last week, but there's going to be a lot of issues with analyzing that data because that PSF is so different from the normal one that we're used to. And also it affects everything in the image. Everything is so bright in these generacy images that you have to deal with these things that we just have
to learn new techniques.
Yeah, exactly. And so
new techniques
I'm just like, great, you tell me what you found and I'll tell people about it.
You need the researchers and you need the people doing the grunt work like that and putting all those papers together. You need the people putting the equipment together that they're using as well. But you also need the people in the field or who can be those at the end, sort of doing a public outreach and sharing the knowledge and explaining in, I guess, layman's terms.
Yeah,
what
but I think
Maddie's working on and what she's doing and why it's important.
Yeah, so like staying connected with that uni system where you can actually get to talk to people about and actually understanding when the scientist tells you what they're doing. Okay, I can be like, okay, I get that, whereas.
Well, I think it's time for your quiz.
Okay, so, I do love trivia, so if I do badly, I will be a little bit devastated.
Well, pop quiz, hotshot. There's a bomb on a bus. Once the bus goes 50 miles an hour, the bomb is armed. If it drops below 50, it blows up. What do? Sorry, no, that's not right. That's from Speed.
That's from Speed, which I haven't seen. So
I've been waiting so many episodes to read that out. So your name starts with an S. The Simpsons.
Okay. Yes. All right. I have watched The Simpsons quite a bit, but I'm not an encyclopedia. Like a friend of mine who was an astronomer that we could.
Oh, when did The Simpsons first air?
Oh, I think 89. So it was the Mary Tyler Moore Show had the first shorts.
Mm-hmm.
It was either very late 80s or early 90s.
So I'm going to say you're right with the year.
Yeah.
Do you know the month?
I think. Was it December?
Oh my gosh! Look at you. So you got 1 point. You've already beaten me. You've already beaten me. The Simpsons theme tune was created in 1989.
Okay.
The same year that The Simpsons was created. How long did it take Danny Elfman to compose the theme tune?
I feel like it wasn't very long. I'm going to say an hour.
Way off.
Oh, okay.
He was quick, but he wasn't that quick.
Okay.
48 hours.
48 hours. That's pretty good.
Homer has an email address, which is a real active account. You can actually send him emails and you'll get an automated reply. What is that email? It's been in a few episodes.
I'm trying to think if it would be more likely to be a personal one or a work one at the power plant. All right, I'm going to go Homer S at springfieldnuclear.com.
Nope.
Chunky
Lover 53.
Of course.
At AOL.com.
AOL, yes, okay, that makes sense.
So I'm going to send an email to chunkylover53 at AOL.com and send it through. I'm definitely going to do that.
Yeah.
Right, so Fox own the rights to The Simpsons. How long do they own the rights to The Simpsons for? There is a year that they become up for grabs again for somebody else to purchase.
I'm going to guess if it came out in 89, 2040?
Nope.
Nope.
Nope. 2082.
Okay, yep.
So in 2082, The Simpsons can be purchased by another company.
Mm-hmm.
Okay, so The Simpsons are yellow rather than another skin tone, I guess, or colour. Why are they yellow?
Yeah, I did know this at some point. Is it just like Matt Groening just wanted them to be yellow and decided that they would be?
No, there's actually a legitimate reason. The Simpsons was created to have yellow skin in a bid to attract attention and make people stop and watch while flicking through TV in the late 80s and early 90s.
Yeah.
So it was done on purpose to catch your attention and go, oh, what's that? That is why The Simpsons are the colour that they are. I would never have guessed that. I never knew that until today. I was 44 years old when I found out that fact about The Simpsons. So,
Yes.
well, look, you won the pop quiz, that's for sure.
Yes.
I got 0, you got 1. So
Yay.
we're like no better than our guests at that.
Yep.
It has been awesome fun.
It's been so
this.
good.
I know.
Yes.
And I think now we should get back to our, what is it? We'll resume normal programming.
Yes.
And yeah, it's been awesome doing this. And thank you for answering my questions. And
That's
it was fun answering your questions.
Yeah, it was good.
And to our listeners, we will see you, or you will hear us, or see us, depends on which platform you watch us on or listen to us on, in the next podcast.
Yeah, which will be soon.
Thanks for listening and supporting us as we continue to learn on our podcast journey. If you would like to contribute to the podcast, you can head to www.patreon.com/Spaghettification podcast and support us for as little as 1 can of beer a day.